Okay, the next in a series, this is the last problem in the problem set from 6.1. It is the ice, the hockey puck that's slowing down. So you're given the mass of the puck, standard puck for you hockey players, 120 grams. Its initial velocity is 6.1 or approximately 120 grams. I think it might be actually a little heavier than that. That might be a randomized number there. Coefficient of kinetic friction between the ice and the puck is 0.15. That is mu k. I should call that V0. Mu k is 0.15. They want us to solve for the time it takes the puck to stop. Okay, to come to rest. So we know our final velocity is, let's see, V is 0. Final velocity is 0. So this is kind of a kinematics problem because if it lets me move just that, I can actually. And then I can move this. Oops. You come down here. The reason I'm doing this is so that you can see, wow, one at a time. These three things are kinematics quantities. I could solve for the time if I only knew acceleration, right? If I knew A, then I would be able to very quickly, knowing that A is equal to the change in velocity over the change in time. If I knew A, I know my delta V already is 6.1, I could solve for delta T. So basically I'm going to use Newton's laws and what I know here to solve for acceleration, and then I'll use this equation to get the time. So I need to start with a force diagram. So what problem is this? This is 616, okay? So I need to start with a force diagram of a hockey puck. The hockey puck has a mass. So there's the Earth's force on the puck, which is the mass of the puck, times that 10.0, or 9.81 we'll use for this, since we're mastering physics. The normal force, the force of the ice, we'll call it, on the puck, is going to be equal and opposite to that guy. Let's say the puck's initial velocity is in this direction. That means the kinetic force of friction, since it's moving, has to be acting in this direction right here. Okay, simple as that. If the velocity is to the right, the force of friction has to be to the left. So that's it. There's no other forces to draw here. There's an unbalanced force. This is the unbalanced force right here. We're going to set the unbalanced force equal to the mass of the puck times the acceleration of the puck. The unbalanced force happens to be the kinetic force of friction. And we'll see that that is the mass of the puck. Let's go one step at a time. Mu k times the normal force, which I call ice on the puck, equals the mass of the puck times A. They gave us this quantity. They gave us this quantity. The normal force, I have to use the relationship with gravity to solve for that, since those two are congruent. Mu k times mass of the puck times G equals mass of the puck times A. Notice they were nice to you and they gave you the mass of the puck. They really didn't need to. It doesn't matter what the mass of the puck is because it cancels out, which you'll see in the coffee cup problem. Same thing is about to happen. So mu k times G equals the acceleration. I think they told us it was 0.15, pretty low because it's ice and cold rubber. 9.81, which is the puck. Let's see what that number works out to be. Here's my calculator. 15% of 9.81 is 1.47 meters per second per second. Now remember, this is our equation. The kinematic equation you might be thinking of looks like this. It's just a rearrangement of that formula up above. I'm going to use this version right here. So I know delta V, this is a negative, by the way, negative 1.47. The reason it's negative is I called my velocity positive in this direction. So my force vector in this direction would be negative. So I really should have had a negative sign out here and all the way down, which I didn't do. So I've got a negative 1.47. So negative 1.47 equals V minus V0 over delta T. V is 0. V0, it starts out at 6.1. So I've got, if I rearrange this, move the delta T over here, divide by negative 1.47, I've got negative 6.1 over negative 1.47. I get 4.15 seconds. Let's see if that works. Okay. All right, I'll let you guys answer the essay part of that question. And does the stopping time of the puck increase, decrease, or stay the same when the mass is doubled? That's kind of interesting. Well, what did we find out here? If the mass cancels out, this is the acceleration relationship right here. You'll notice mass is not a part of that. So I'll let you answer that question if you think that the stopping time of the puck changes. I'm going to let you work on that with the acceleration that we just found. The formulas can be rearranged to give you something close to that. Okay? All right, I'm going to do the last one, the coffee cup problem, on a separate screencast.